guys, how are you doing? I'm great, and my hair is not greasy, it's wet. So, today I'm going to read to you lectures on physics by Richard Feynman. He was a Nobel laureate and he's a theoretical physicist. So I guess that his lectures are interesting. And so let's get started maybe. The first section is called Atoms in Motion. Introduction. This 2-year course in physics is presented from the point of view that you, the reader, are going to be a physicist. This is not necessarily the case, of course, but that is what every professor in every subject assumes. If you are going to be a physicist, you will have a lot to study. 200 years of the most rapidly developing field of knowledge that there is. So much knowledge, in fact, that you might think that you cannot learn all of it in 4 years, and truly you cannot. You will have to go to graduate school too. Surprisingly enough, in spite of the tremendous amount of work that has been done for all this time, it is possible to condense the enormous mass of results to a large extent. That is, to find laws which summarize all our knowledge. Even so, the laws are so hard to grasp that it is unfair to you to start exploring this tremendous subject without some kind of map or outline of the relationship of one part of the subject of science to another. Following these preliminary remarks, the first 3 chapters will therefore outline the relation of physics to the rest of the sciences, the relations of the sciences to each other, and the meaning of science to help us develop a feel for the subject. You might ask why we cannot teach physics by just giving the basic laws on page 1 and then showing how they work in all possible circumstances, as we do in Euclidean geometry, where we state the axioms and then make all sorts of deductions. So, not satisfied to learn physics in 4 years, you want to learn it in 4 minutes. We cannot do it in this way for 2 reasons. First, we do not yet know all the basic laws. There is an expanding frontier of ignorance. Second, the correct statement of the laws of physics involves some very unfamiliar ideas, which require advanced mathematics for their description. Therefore, one needs a considerable amount of preparatory training even to learn what the words mean. No, it is not possible to do it that way. We can only do it piece by piece. Each piece or part of the whole of nature is always merely an approximation to the complete truth, or the complete truth is truth so far as we know it. In fact, everything we know is only some kind of approximation, because we know that we do not know all the laws as yet. Therefore, things must be learned only to be unlearned again, or more likely to be corrected. The principle of science, the definition, almost is the following. The test of all knowledge is experiment. Experiment is the sole judge of scientific truth. But what is the source of knowledge? Where do the laws that are to be tested come from? Experiment itself helps to produce these laws in the sense that it gives us hints, but also needed is imagination to create from these hints the great generalizations, to guess at the wonderful, simple, but very strange patterns beneath them all, and then to experiment to check again whether we have made the right guess. This imagining process is so difficult that there is a division of labor in physics. There are theoretical physicists who imagine, deduce, and guess at new laws, but do not experiment, and then there are experimental physicists who experiment, imagine, deduce, and guess. We said that the laws of nature are approximate, that we first find the wrong ones, and then we find the right ones. Now, how can an experiment be wrong? First, in a trivial way, if something is wrong with the apparatus that you did not notice, but these things are easily fixed and checked back and forth. So, without snatching at such minor things, how can the results of an experiment be wrong? Only by being inaccurate. For example, the mass of an object never seems to change. A spinning top has the same weight as a steel one. So, a law was invented. Mass is constant, independent of speed. That law is now found to be incorrect. Mass is found to increase with velocity, but appreciable increases require velocities near that of light. A true law is, if an object moves with a speed of less than 100 miles a second, the mass is constant to within 1 part in a million. In some such approximate form, this is a correct law, so in practice one might think that the new law makes no significant difference. Well, yes and no. For ordinary speeds we can certainly forget it and use this simple constant mass law as a good approximation, but for high speeds we are wrong, and the higher the speed, the more wrong we are. Finally, and most interesting, philosophically we are completely wrong. With the approximate law, our entire picture of the world has to be altered, even though the mass changes only by a little bit. This is a very peculiar thing about the philosophy or the ideas behind the laws. Even a very small effect sometimes requires profound changes in our ideas. Now, I'm interested to know what is there. I cannot somehow. Okay. Now, what should we teach first? Should we teach the correct but unfamiliar law with its strange and difficult conceptual ideas? For example, the theory of relativity, four-dimensional space-time, and so on? Or should we first teach the simple constant mass law, which is only approximate but does not involve such difficult ideas? The first is more exciting, more wonderful, and more fun, but the second is easier to get at first, and is the first step to a real understanding of the first idea. This point arises again and again in teaching physics. At different times we shall have to resolve it in different ways, but at each stage it is worth learning what is now known, how accurate it is, how it fits into everything else, and how it may be changed when we learn more. Let us now proceed with our outline or general map of our understanding of science today, in particular physics, but also of other sciences on the periphery, so that when we later concentrate on some particular point, we will have some idea of the background, why that particular point is interesting and how it fits into the big structure. So, what is our overall picture of the world? Matter is made of atoms. This is the title. If in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, or the atomic fact, or whatever you wish to call it, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see that there is an enormous amount of information about the world if just a little imagination and thinking are applied. To illustrate the power of the atomic idea, suppose that we have a drop of water a quarter of an inch on the side. If we look at it very closely, we see nothing but water, smooth, continuous water. Even if we magnify it with the best optical microscope available, roughly 2000 times, then the water drop will be roughly 40 feet across, about as big as a large room, and if we looked rather closely, we would still see relatively smooth water, but here and there small football-shaped things swimming back and forth. Very interesting. These are paramecia. You may stop at this point and get so curious about the paramecia with their wiggling cilia and twisting bodies that you go no further, except perhaps to magnify the paramecia still more and see inside. This, of course, is a subject for biology, but for the present we pass on and look still more closely at the water material itself, magnifying it 2000 times again. Now, the drop of water extends about 15 miles across, and if we look very closely at it, we see a kind of teeming, something which no longer has a smooth appearance. It looks something like a crowd at a football game as seen from a very great distance. In order to see what this teeming is about, we will magnify it another 250 times, and we will see something similar to what is shown in figure 1.1. This is a picture of water magnified a billion times, but idealized in several ways. In the first place, the particles are drawn in a simple manner with sharp edges, which is inaccurate. Secondly, for simplicity, they are sketched almost schematically in a two-dimensional arrangement, but of course they are moving around in 3 dimensions. Notice that there are 2 kinds of blobs or circles to represent the atoms of oxygen, black, and hydrogen, white, and that each oxygen has 2 hydrogens tied to it. Each little group of an oxygen with its 2 hydrogens is called a molecule. The picture is idealized further in that the real particles in nature are continually jiggling and bouncing, turning and twisting around one another. You will have to imagine this as a dynamic rather than a static picture. Another thing that cannot be illustrated not drawing is the fact that the particles are stuck together and they attract each other, this one pulled by that one, etc. The whole group is glued together, so to speak. On the other hand, the particles do not squeeze through each other. If you try to squeeze two of them too close together, they repel. The atoms are 1 or 2 multiplied 10. How to say it? In -8 degree. I don't know if it's the same in English. Like it's 10 in -8. You know this? 10 and -8. In the upper right corner of the number, is it called a degree? Centimeters in radius. Now 10 in -8 centimeters is called an angstrom, just as another name. So we say they are 1 or 2 angstroms in radius. Another way to remember their size is this: if an apple is magnified to the size of the Earth, then the atoms in the apple are approximately the size of the original apple. I'm sorry, I don't know how to say some things in English. I will see after this video is made. Now imagine this great drop of water with all of these jiggling particles stuck together and tagging along with each other. The water keeps its volume. It does not fall apart because of the attraction of the molecules for each other. If the drop is on a slope where it can move from one place to another, the water will flow. But it does not just disappear. Things do not just fly apart because of the molecular attraction. Now the jiggling motion is what we represent as heat. When we increase the temperature, we increase the motion. If we heat the water, the jiggling increases and the volume between the atoms increases. And if the heating continues, there comes a time when the pull between the molecules is not enough to hold them together, and they do fly apart and become separated from one another. Of course, this is how we manufacture steam out of water. Oh, I'm sorry. I'm sorry. I didn't turn off the volume. Of course, this is how we manufacture steam out of water, by increasing the temperature. The particles fly apart because of the increased motion. In figure 1.2 we have a picture of steam. This picture of steam fails in one respect. At ordinary atmospheric pressure, there certainly would not be as many as 3 water molecules in this figure. Most squares this size would contain none, but we accidentally have 2.5 or 3 in the picture, just so it would not be completely blank. Now, in the case of steam, we see the characteristic molecules were more clearly than in the case of water. For simplicity, the molecules are drawn so that there is a 120 degrees angle between the hydrogen atoms. In actual fact, the angle in 105 degrees. 3, I don't know this, what it is. 3 and a little dash there. degree. And the distance between the center of the hydrogen and the center of the oxygen is 0.9557 E. So we know this molecule very well. Let us see what some of the properties of steam vapor or any other gas are. The molecules being separated from one another will bounce against the walls. Imagine a room with a number of tennis balls, 100 or so bouncing around in perpetual motion. When they bombard the wall, this pushes the wall away. Of course, we would have to push the wall back. This means that the gas exerts a jittery force which our coarse senses, not being ourselves magnified a billion times, feel only as an average push. In order to confine a gas, we must apply pressure. Figure 1.3 shows a standard vessel for holding gases used in all textbooks. A cylinder with a piston in it. Now it makes no difference what the shapes of water molecules are, so for simplicity we shall draw them as tennis balls or little dots. These things are in perpetual motion in all directions, so many of them are hitting the top piston all the time that to keep it from being patiently knocked out of the tank by this continuous banging, we shall have to hold the piston down by a certain force, which we call the pressure. Really, the pressure times the area is the force. Clearly, the force is proportional to the area, for if we increase the area but keep the number of molecules per cubic centimeter the same, we increase the number of collisions with the piston in the same proportion as the area was increased. Okay, so I think we can stop here. So thank you very much for listening and watching maybe. So